In our next section here, we're going to talk about a general overview of how IPv4 route redistribution works. We'll come back a little bit later and talk about IPv6 redistribution because there are some minor caveats and differences between the two implementations. But specifically in this section, we're going to talk about just in general how route redistribution works. And then most importantly, how the router or how iOS specifically is going to choose one path over another. And then when we're looking at multiple paths to the same destination, how are we actually going to make this decision by looking at the administrative distance? Now, we'll see in general, the administrative distance is going to be one of the big issues that we need to take into account when we're doing redistribution, because there's some cases where the distance will automatically prevent problems for us, but there are some cases where the distance will cause a problem for us. So we need to talk about the differences between a metric-based loop and an administrative distance-based loop, because there's different ways that you would see the symptoms either in the control plane or the data plane, and then there's different types of resolutions that you would need to use for one versus another. Now, from a very general overview to start, when redistribution actually occurs, and we're assuming that we know what redistribution is basically taking routes from one protocol and then adding them to another protocol or advertising them to another protocol. So if you're running OSPF on one interface, you're running EIGRP on the other interface. Since it's not the same protocol, they don't automatically exchange the information. So redistribution is the way to take the routes from OSPF and to advertise them to EIGRP and then vice versa. Now, we'll see the big issue that we run into when we do redistribution, though, is that the visibility within the protocol end-to-end is lost. So OSPF cannot run SPF on an EIGRP route, or EIGRP cannot run dual on an OSPF route. So we'll see that there are problem cases, but in general, these should be preventable to begin with, and that's going to be one of our big focuses in these next sections. Now, specifically when we're implementing redistribution, one thing that is very key to understand here is that the redistribution process happens from the RIB, or the routing table, and not from the routing database. So this means that if you are learning routes through OSPF or you are learning routes from EIGRP, but for some reason they're not actually making it to the routing table, those routes are not candidate for redistribution. So simply you would look at the show IP route output, show IP route OSPF, show IP route EIGRP, and that ultimately determines which routes can even be redistributed to begin with. Now, specifically, there's going to be two cases that we're going to see that happens when redistribution occurs. We're going to take the routes that are installed in the RIB or installed in the routing table as that protocol, and we're also going to take the connected interfaces that are running the protocol. So, for example, if we were to take a look at a very basic case where maybe we have OSPF on one interface, let's say on router 1 over here we have OSPF, and then on another interface we have EIGRP, and we're doing mutual redistribution, or in other words, two-way redistribution between the protocols, taking OSPF and redistributing it into EIGRP and then back. This means that when router 1 takes the routes and introduces them to the EIGRP topology database, it's going to take anything that is reachable via the interfaces running OSPF, so what we see when we show IP route OSPF, but then also those connected links. So gig 1.100, or in this case the DMVPN tunnel interface, whatever has the OSPF process enabled on it, if you were to look at the show IP OSPF interfaces or show IP OSPF interface brief. Now the same would be true for EIGRP back into OSPF. We would look at what is in show IP route EIGRP, and then we would also look at show IP EIGRP interfaces. Because as we'll see as we talk about administrative distance, a connected route will always be preferred over any dynamic route, because if that is your physical segment, you should route to that link as opposed to going to some other router in order to reach that connection indirectly. So this is one of the key points we first have to understand, that the redistribution is happening from the RIB. It is not happening from the routing database. So not from the OSPF RIB, not from the BGP RIB, it's the general global routing table when we look at show IP route OSPF, show IP route EIGRP. Now, to determine which routes actually make it into the table, we have to understand how the routing advertisement rules work differently with different protocols. And in general, you can group these into two different types, which are distance vector and not distance vector. Now, in the case of RIP and EIGRP, which are distance vector protocols, in order to guarantee that the path is loop-free end-to-end, they actually have to be routing that destination through the protocol. So for EIGRP, for example, if I'm learning a route and I calculate the feasible distance end-to-end on it and I create a successor in the EIGRP database and say that I'm going to install this in the routing table, but then later a new route comes in with a lower administrative distance, or maybe I configure a static route, and now the feasible distance for EIGRP becomes infinite or inaccessible, which means that I cannot install it in the routing table, which means I cannot advertise it to any neighbor, which also means I cannot perform redistribution for it. Now, in the case of OSPF and BGP, this works a little bit differently because there's a separation between the routing database and then the actual RIB or the forwarding table. In the case of OSPF within an area, assuming we're performing the actual SPF calculation end-to-end, you can redistribute, or I should say not redistribute, you can advertise a route that you're not actually using. And the same case is true with BGP. BGP will call this a RIB failure, where it's warning you that if you don't actually install the route through BGP but you continue to advertise it, you could potentially have a loop in the data plane. So we'll see as we start to get into the details later, this results in some interesting cases where OSPF might cause a loop where EIGRP wouldn't, or RIP might cause a loop where BGP wouldn't, simply depending on the routing protocols have different advertisement rules. Now, ultimately, we should be able to predict these before we even do the redistribution and get to the point where we can say, here's going to be the loop, this is specifically how I'm going to prevent it, and then I'm going to prevent it in the implementation before I even see the issue in the control plane or the data plane to begin with. Now, in the case of the connected routes, as I mentioned, when we're going from one protocol to another, so in this case, let's say we're going from EIGRP into OSPF, the router will take its connected link that is running the EIGRP process. Now, in IPv6, this is going to work a little bit differently. This does not happen by default, but you do have the option to do that. But in IPv4, it will implicitly include the connected interface. Now, you may or may not want this. So in the case of iOS for IPv4, it gives you the control to choose whether you want the connected redistribution to happen. So in this case, if we were to simply say redistribute EIGRP into OSPF and OSPF back into EIGRP, it means that this router here that's in the OSPF domain will have a route to that connected link of router 1. And likewise, another router in the EIGRP domain, for example, router 6, should know the route to the connected link of router 1. Now, there might be cases where you don't want this, though. Because if the link is just used for transit, we don't actually need a route for it, we just need a route through it. And this will make more sense once we start to talk about different types of tunneling techniques and different types of MPLS tunneling techniques, where as long as we can get the traffic to the edge, we don't necessarily need to know the details of the core in the middle. So we may only want to advertise the final destination through redistribution and not necessarily the connected links. And in that case, iOS gives us that control. But the key point to remember is that this does not happen automatically. That when you redistribute EIGRP into OSPF and back, it will include the connected links. If you want to filter them out, you have to explicitly exclude them. So the way that we would do this is by saying redistribute connected, and then use a route map to deny the connected link from going into the destination protocol. So this essentially would override then our implicit redistribution when we're saying under the EIGRP process, redistribute OSPF. Now, we could also see that there might be cases where if you didn't know this, that you could break connectivity because you are overriding the implicit redistribution. So when we take a look at this on the CLI, we'll see that what the end results are, what happens when we're redistributing dynamically, but we're also redistributing connected. There can be some cases where you break the network by actually doing that. Then we need to think about how is the router actually choosing which path actually gets to the RIB. Now, within an individual protocol, we know that there's a decision process that's happening inside of the database. For example, EIGRP is using the diffusing update algorithm. OSPF is using shortest path first. Then they're choosing one or more best paths. In the case of EIGRP, these best paths could be equal cost or they could be unequal cost, as long as we have feasible successors and we have variants configured. In the case of OSPF or most other protocols, they would simply be equal cost for ECMP, for equal cost multipathing, and then we're going to present those to the routing table. Now, whether we actually install these into the RIB or into the routing table is going to depend on if we have multiple equal cost matches, or I should say not equal cost, multiple equal longest matches to the destinations between multiple protocols. In that case, then we're going to use the administrative distance to determine which one actually gets installed. Now, as we'll see once we go through the actual redistribution, this is a very key important point to remember, that the administrative distance only comes into play if the destinations are equal longest matches. So if I have 2/24s for the same prefix, one via OSPF, one via internal EIGRP, I would choose the internal EIGRP route. However, if I had a /25 from OSPF, I would install the /25 and the /24 from EIGRP, but when I actually go to route the packets, I would prefer the longer match, the 25 over the 24. So we'll see that this can be actually one of the tools that we can use to fix redistribution problems by hiding the details of the topology with shorter matches, or by leaking longer matches to redistribution in order to force traffic to go one direction. But the end result of that is that the route gets installed to the routing table, which is the RIB, and then normally gets installed into the forwarding table, the FIB or the CEF table, in order to actually forward the traffic. Now, in the case that we have the same protocol and we have equal longest matches, but what if we have multiple processes? So let's say, for example, we have EIGRP AS1 and we have EIGRP AS2, and we have two equal longest matches, and they have this, and we're trying to choose one over the other. In that case, and it's not really documented this way, in this case we're going to choose just whatever the lowest process ID is. So if we have OSPF1 versus OSPF2, we're going to choose OSPF1. If we have EIGRP AS100 versus 200, we're going to choose AS100. Because internally, the routing process has to have some sort of tiebreaker in order to install the route in the RIB. Because if it's installed out multiple interfaces and we're not actually doing ECMP, that's where the router could potentially cause a loop in the data plane. So we'll see, to understand this, you do need to know what are the administrative distance values for the protocols. Now, this is documented somewhere in the documentation. I don't know exactly where offhand it is, but I would say that this is something that you should just basically memorize to know what are the differences between the protocols. Now, you can, of course, look at the routing table, and the routing table will tell you what the AD is, but there is a specific reason why the routing process is ordering the routes in this order. So first, we have our connected prefix with a distance of 0. Those will always be preferred over anything else. So if I have a /24 connected and I'm learning an OSPF route, the OSPF route never makes it to the RIB, so I'm not actually going to use it. Which makes sense, because if I'm already on that segment, I should just directly route to it. I shouldn't indirectly route to it through somebody else. Now, a static route is next, because if you're configuring it manually, it means you're trying to override whatever the default behavior is. So if I have an OSPF route and I have a static route, assuming that they are equal longest matches, then we're going to prefer the static over the OSPF. Now, in the case of static routing, as we saw, that you can manually set this, which is called a floating static route. So you could configure a static route with a distance of 111, which means that the OSPF route would be preferred first, but then we would fall back to the static route if the OSPF route went away. Now, we'll see changing the administrative distance is actually going to be one of the tools or one of the mechanisms that we have in order to prevent issues in the control plane during redistribution, or in order to solve data plane loops that we cause by doing the redistribution wrong. So without going through all the details of all of the numbers here, let's think about, just from a high-level value, why are these the distance values? So for example, why do we choose an external BGP route first over an internal BGP route or over an IGP? Well, think about it. If we're an edge router and we're learning a route from external BGP, and we're also learning the route from an IGP. Let's say that we did redistribution of BGP into OSPF, so we're at the edge and we have the eBGP route and we have the internal route. Now, as we can see here from the distance table, BGP is less BGP is more preferred in this case, the external BGP with a distance of 20 versus any of the IGPs, and also versus internal BGP. And the reason simply is that if you are learning the route from eBGP, it means it's not your destination. It's someone else's destination on the internet. Because if it was your destination and you were learning it through BGP, you would normally be learning it from IBGP. So from a basic logic point of view, it wouldn't make sense to route into the network in order to get to an external destination. We should route out of the network to get to an external destination. Where the opposite is true for the internal BGP route. If we're comparing an IBGP route versus an IGP, IGP will always have better visibility of internal routing than IBGP will, because IBGP doesn't understand what the physical topology of the network is. Because IBGP or eBGP, these are logical constructs where we're doing maybe a multi-hop peering or just some sort of TCP connection between the routers in order to exchange the reachability information. Where in the case of OSPF, OSPF does have an exact map of the internal network. Or EIGRP can perform the feasibility condition on all of the internal routes. So in general, then it would make more sense to choose the external BGP route first, because it means it's a route on the internet. It's not a route internal to your network. Now, we will see that there are cases where this might not be true, but in general it is true. These corner cases might be like MPLS Layer 3 VPN, where we're doing an eBGP peering to the service provider, but then we also have a backdoor link that we're learning the route from IGP. And if we want to prefer the backdoor link over the MPLS route, then we would have to modify the administrative distance either globally or on a per prefix basis in order to choose one versus another. So keep in mind here that these distance values, these are just the defaults. We can change these to whatever we want, and we can also change it on a per prefix basis. Now there are some caveats and some minor limitations, but in general you can pretty much get the distance to do whatever you want. Okay, so after BGP, let's think about EIGRP versus OSPF. Why would we want to choose an EIGRP internal route with a distance of 90 versus an OSPF route with a distance of 110? Now, assuming both of the routes are internal, then the decision is technically arbitrary, because EIGRP should be loop-free based on dual, and OSPF should be loop-free based on SPF. But the real issue we run into is that OSPF doesn't automatically separate the difference between internal routes and external routes from a perspective of the administrative distance. So this means that if the router was looking at an internal EIGRP route versus an external OSPF route, we would prefer it to choose the internal EIGRP, because the feasibility condition is running end-to-end on that prefix, and we've already guaranteed that it's loop-free. In the case of external OSPF, that might not be the case. And we'll see some of those cases today where you can give the router the route that is the wrong information, and if it chooses the wrong information over the correct information, either we can create a loop in the control plane where the route flaps back and forth, or we can create a loop in the data plane where the trace goes infinitely until the TTL expires, or that we're just not able to route to the destination at all. Now another case here would be the opposite of this. So we're preferring internal EIGRP versus the other IGPs, but the opposite is also true. We're choosing external EIGRP last after the other IGPs. Because again, the issue is the route is probably not within your own routing domain. If you are learning the route externally versus internally, the internal protocol is already going to have more visibility about the state of the network than the external protocol is. So we'll see this is the main issue with redistribution, that when you move the routes from one protocol to another, SPF and dual, they're not compatible to each other. So dual cannot say the SPF guaranteed the route is loop free, and then I will also agree with that through the feasibility condition, or vice versa. So since we're losing the visibility when we're going into the external prefixes, that's why we would always want to prefer the internal routes over the external routes, with the exception of BGP, because BGP is not supposed to be used to route our internal network. IGP routes our internal network, BGP routes to external domains. Okay, there's a couple questions here. Is there a particular reason why they didn't make external OSPF routes a different administrative distance? Honestly, I don't really know the answer to this, but you can do it manually if you want. So you can get the same effect as EHRP does, where you could separate your internal versus external routes, and then say maybe internal OSPF is 110 and external OSPF is 169, so maybe it's more preferred than external EHRP. So you can do that, and there's cases where it will fix a problem, but the issue is that with the code base now, it's too late to make that change. Because think about if you have one router that is disagreeing at the administrative distance of the other ones, it could have a big impact on the routing table. So simply based on the fact that that was the default to begin with, it's too late to change it. Now again, you can do it manually. If you go to all of the routers in the topology and say that these are the distance values that I want to use in my network, that's fine. But from a default point of view, they can't really make the change because that there's too many potential things that it could impact. Okay, there's a question. I have a confusion with this with eBGP over iBGP due to administrative distance. So why is the best path selection a step that prefers eBGP over iBGP? Isn't it redundant? Okay, that's actually a good question, and technically it's not a redundant step because there's a difference between the BGP rib and the global rib. Now, we'll talk about this in more detail when we talk about BGP and specifically its path selection and how best path selection works. But as part of the path selection rules internal to BGP, it says prefer an external path over an internal path. But in this case, we're not really trying to prefer BGP over BGP. We're trying to say that BGP is preferred over IGP, and then IGP is preferred over internal BGP. So it's not an issue with BGP versus itself, it's an issue with BGP versus other protocols. That eBGP should be preferred over IGP because if you're learning it externally, it's not your route. Then vice versa. If you're learning it through IGP and iBGP, it is your route, and then you should route internally through the IGP because it's going to have better visibility end to end. Okay, someone had mentioned here under this document, which is under BGP, what is administrative distance? It's under the technology documentation under IP routing, and it shows what the distance table is. The only issue with this, though, is that this document is under the technology documentation and not the product documentation, so you might not have access to it in the exam. So I would say that as a general rule, you should know these values offhand, because when you're going to do redistribution, if you don't know which one is actually going to be preferred, then you're not going to be able to make the correct prediction of what the behavior should be.